Circuits. An electric circuit is an external path that charges can follow using a conducting material. For charge to flow, the path must be complete and unbroken. An example of a conductor used to form a circuit is copper wire. Continuing the water analogy, one can think of a wire as a pipe for water, or charge, to move through. The circuit above consists of one battery, a light bulb, and connecting wires. The conventional current leaves the positive terminal of the battery, goes through the light bulb, and returns to the negative terminal. Conservation of electric charge is the idea that the amount of charge in an isolated system never changes. In fact, the amount of positive charge and the amount of negative charge in the universe never changes. In a closed circuit, the amount of electrons does not change. Light bulbs do not use up electrons. The same amount of electrons go in one side and out the other, through the battery, then back through the circuit. So the same number of electrons are going into the light bulb as are leaving the light bulb. And why have I drawn the arrows this way? Why are the electrons moving in a counterclockwise direction? Electrons flow in the opposite direction to conventional current. In the circuit on the left below, negative charges flow through the circuit since there is an unbroken path and there is an electric potential difference. If you take away the battery, shown here, there's no electric potential difference. There's no difference in voltage. Therefore, there's no current. This would be like having a lake of charges versus a waterfall of charges. Something to note is that electrons in a wire actually do move around, even without an electric potential difference. As we previously learned, particles that are at room temperature move around due to having kinetic energy. If you have a glass of water on the table, the water molecules are still moving around randomly inside the glass. Below, the electrons inside this wire are having collisions with atoms in the wire. However, these movements are random in all directions, and therefore the electrons don't go anywhere in particular. They don't flow in one direction. It is not until you add a source of electric potential difference that an electric field is created, which then pushes the electrons around the circuit in the same direction. This is why when you flip a light switch, all of the bulbs light up instantaneously. The electrons that are currently in the wire immediately feel the electric force due to the new electric field and start to move in the same direction. Each electron is still bouncing around in all directions, but they also feel an electric push, which causes their motions to, on average, go in the same direction, but relatively slowly. This is called their drift velocity. So instead of just bouncing around in all directions, they'll start to average out to being in one direction, like how this electron is bouncing through this wire. To light up a light bulb, certain things need to happen. First of all, the circuit cannot have gaps. So here is a gap. And these are all, by the way, these are all pictures from a FET simulation. In the circuit to the right, conventional current is moving counterclockwise out of the positive end of the battery this way. The electrons are actually moving the other way, out of the negative terminal through the light bulb and back into the positive terminal. So these electrons leave the battery, they move through the light bulb's filament, using up their energy, and then they return to the battery to refill their energy. The bulb has to complete the circuit, otherwise no current will go through it. If you attach the light bulb as shown to the right, the current will flow through the wires, like this, and not through the light bulb. This is called causing a short circuit. You can see that the battery would then be on fire in this FET simulation, and that's because we have very little resistance, but we have a potential difference. Even connecting an alternate path for charge to flow through the light bulb, as shown here, still won't work. If there is a path with zero resistance, the electrons will take it. So here, they're not going to bother going this long way with resistance when they can easily do a shortcut here. But do note, Wires themselves do actually have some resistance. However, we usually solve circuit problems as though they don't. Let's review what we've learned about current in circuits so far. A battery acts like a pump, pushing charge through the circuit. It is the circuit's energy source. Charges do not experience an electrical force unless there is a difference in electrical potential, also known as voltage. Therefore, batteries have a potential difference between their terminals. The positive terminal is at a higher voltage than the negative terminal. The greater the voltage difference, the greater the current. We will be using specific symbols to represent parts of a circuit. Below, you can see some of these symbols. Both of the pictures below represent the same circuit that includes one battery and one light bulb. Here is the symbol for a battery. It's one long line next to one short line. Long line, short line. The long line represents the positive terminal of the battery. Any lines like this, shown here, are wires that are connecting elements together. Light bulbs can be represented in a variety of ways, but here's 4 possible options. I tend to draw my light bulbs like that, but I've also seen them with the X many times, so any of these will work. To measure the current going through a circuit, you need to connect an ammeter. The ammeter must complete the circuit so that all of the charges are flowing through the ammeter. The circuit above has one branch, which means all of the current is going through the same path. The ammeter, represented by an A with a circle around it, is connected into the circuit. Ammeters have very low resistance so that they don't affect the amount of current in the circuit. This ammeter will not measure the current going through the light bulb, and in fact is very dangerous as most of the current will go through the ammeter and destroy it. Since ammeters have very low resistance, the current's going to go this way instead of through the light bulb, and it's going to potentially destroy the ammeter.